Right on. Ooh, that's loud. Hi. So, like he said, I'm Geoff Gerrietts. I'm a development manager at AppNeta. I've been a Pythonista for 15 years, and I've been doing web development pretty much as long as that was a thing. Before I go on, I ought to call out that both the Boston Python meetup and my team at AppNeta really did a great job helping me with these slides, so it's all about the delivery now. So they tell me that I ought to tell you what I'm going to tell you, and so I'm going to tell you what I'm going to tell you. And that is, first, that performance matters, but it's hard to do right. And there are a lot of tools that will help you with that, and you should use them all. As a caveat, I will say that I'm mostly talking about server-side performance of web applications today. User experience is very important, but it has different tools and technologies. Be a totally separate talk, okay? So performance matters, and the thing is that it's been hard historically to say how much it matters. I mean, features have obvious value. That's what I've been working on for most of my career. And even in software processes that identify performance constraints as something that should be called out in a feature description, it's really very hard for product management to specify what those performance constraints ought to be, or for that matter, understand what can go wrong with the performance. And sometimes that's because we haven't known the value. Now, in the last several years, big retail has brought a lot of focus on performance because they were able to identify that low latency correlates with increased conversion and revenue. Amazon and Walmart in particular released studies that showed that as little as 100 milliseconds of response time could have a 1% impact on your total revenue. Google, Yahoo, and Mozilla also produced performance studies that have had similar results. And the burden of performance doesn't all fall on the product management team, though. In development, we have, I think rightly, had a culture that chooses readable, maintainable code over the most optimal code, under the understanding that it is really hard to figure out what pieces of your code need to be high performance before that code is deployed and shown to be not performant enough. On the other hand, you also frequently only get one chance to do it right, which is a pretty vicious trade-off. So performance does matter, though, because we all know that slow websites erode your sanity, and they cost you money. So the lesson of the first part is that the most common mistake in performance analysis remediation is just ignoring it, or maybe better put, not recognizing the impact performance has on your bottom line. Once you start to think about it, though, there's still plenty of mistakes to make. So bureaucracy is the art of organizing an enterprise such that the buck never lands on your desk. And most organizations do some of that, right? The developer points at the database, the DBA points at the hardware, the sysadmin points back at the code. It's the circle of blame. And I've been that guy. I've been the guy that expects the DBA to fix all my performance problems by putting better indexes on his tables. But honestly, we all have to recognize at some point that the indexes can't save us. We need to write better queries. We need to have better caches. We need to ask not what our database can do for our app, but what our app can do for the database. So the Drunken Man approach is a little bit different. That's where you come up with a plausible idea to improve your performance. You go do it and maybe measure the results if you can, and I don't know, things might have got better. So this model was suggested by Brendan Gregg, who is a security researcher at Netflix. He's the guy that did Screaming at the data center. If you saw that video, it's fascinating if you haven't. But the thing about the Drunken Man is even when it works, it might not be addressing the most important performance problems you have. Now I get to tell a story. I worked at a certain company that I definitely won't name for fear of litigation, that spent 2 months of maybe 4 or 5 engineers at a time working on a project to consolidate and uglify our JavaScript and CSS under the theory, a strong theory, a dominant theory in the web space, that the number of requests that clients had to make in order to retrieve the assets were negatively impacting consumers' ability to use the site. And so after it was all done, we did some comparison measurements and discovered that there was actually no measurable improvement. We could not get a statistical indication that we had helped things at all. But we did manage to spend a couple $100,000 not doing anything. It was pretty cool. The idea is, if you're designing a project before you know which parts of the app need attention, you're the drunken man. Put down the bottle, or the flask, or the pyramid, and step away from the backlog. The last common performance anti-pattern that I've seen is what I call the hammer. Passing the buck's bad, shooting in the dark is bad, and so looking for some amount of insight is always a good first step. But when you've only got one tool and it's a hammer, every problem starts to look like a thumb, right? This problem happens when you lean too heavily on 1 or 2 tools. You can't see into their blind spots. And if there's a theme that I'm going to be developing today, it's that one tool is never enough. The story time here, I worked with a sysadmin who had Oracle writing its tables to a network-attached storage device over NFS. And according to his tools, which were top and ifconfig, this system was awesome. It had no problems at all. Now, if you were a user on the website, you had a different opinion of how successful this build was, but getting the sysadmin to admit that there might be a problem with this strategy took a great deal of time and effort. And that's because he just didn't have the right tools. He didn't know that what he was looking at, or that the average query time was significantly slower. So all 3 of these anti-patterns have sort of a common flaw. They stop short of discovering the root cause of the latency in your system. Just like fixing bugs, because performance problems are essentially bugs, if you don't find the root cause, you don't understand the problem. And if you don't understand where the latency is coming from, you really can't meaningfully address it. So for most of us, well, maybe, for some of us, the first place our head goes when we start talking about finding latency is to profilers, right? And there's a good reason for that. That's because profilers are extremely powerful. They've been the go-to tool for performance analysis for decades. And you got to be careful, because the profiler can become a hammer pretty quickly, right? A profiler is really best used to analyze a specific code path. So this is an approach that we used, again, at an unmentionable former employer, to try to use profilers to find performance problems. The idea was that we would just stick a profiler between Django and our application code, and then just dump the profiling stats out. And that's not a bad idea, but the trouble with profilers, particularly line profilers, the kind that Python has built in, is that each time you call a function, the function has to call out to the profiler to say, hey, I'm starting this function, and each time you come back from the function, it sends another call out to and the profiler is writing these stats out to the file all the time, which puts a bunch of I/O overhead into your application that previously didn't exist on every function call, and it puts a bunch of function call overhead just passing those stats into the profiler. And so profilers, you can't run this in production. You can't run a traditional line profiler in production. It will take your application down very quickly, and that's something I've seen before. But the other thing that's interesting is that because of the amount of overhead involved in actually recording the profiles, you can distort the picture of where the latency is actually coming from. Right? The really tiny little function call that only takes a microsecond now takes a couple of milliseconds instead. And the great big honking guy that's taken a second and a half it doesn't have nearly as much overhead added to it. And so it distorts the picture a little bit. Maybe not a big deal. Who knows? All right. Oh, look. It's time for story time again. So in this place where we used where we stuck that profiler in the middleware, we were trying to address the fact that the Django app was pretty slow, right? And so one of the roots of the investigation we used was the profiling. Of course, we couldn't profile in production, so what we did was we used the Apache logs to try to simulate traffic distribution. Now, the trouble with that is that get and query parts, those you can get, but the post data isn't there anymore. So we would have troubles where we couldn't distinguish why one URL would take maybe 500 milliseconds on a couple of calls and 3 seconds on the other, because that was all relative to what was the content of the post. Eventually, we ended up only testing the assumptions. It was not a very useful experiment. Now, there is a way to use profilers responsibly. There are actually a couple of ways. One of them is to use it to actually inspect a code path that you've already begun identifying as a problem spot. They're fantastic at doing that, and it can show you that the while loop that you thought was completely innocuous is actually deeply nested and has n-squared behavior, right? There's also another way to use profilers in production, and that is statistical profiling. And statistical profiling uses periodic random sampling to build the profiling data. It's inexact, but it produces a statistically accurate model of where your code is spending time by sort of randomly checking every once in a while. So this is a fairly common architecture, right? You've got a load balancer, some app nodes, maybe a MySQL and a Memcache playing cat's cradle with the app. And when you statistically profile, essentially you put a statistical profiler on each of those app nodes, and they sample everything in there. That provides some big picture, but it lacks context. You don't know why a particular call that's taking a great deal of time takes a great deal of time. And you especially don't know if you've got a call that sometimes takes a lot of time and sometimes takes a little time, why that's the case. You just know that the average latency is pretty poor, right? Still useful, but it does have some significant blind spots, right? So maybe when I start talking about quantifying latency, your mind doesn't go to profilers. Maybe it goes to top or strace. Maybe secretly you're a system administrator. That's okay. We like you. And there's actually perfectly good reason for you to think this, right? The operating system provides a ton of tools. I mean, like, look at this graph, right? It's crazy. You probably want to look at it after the conference, though. It's pretty detailed. I stole this from one of Brendan Gregg's talks on Linux system optimization. It shows various parts of the system and the tools that can provide insight into that system. And these tools are great. Most of them also work just fine in production, right? But you remember this architecture? So when you're using these kinds of tools, that graph is on every one of those nodes, right? And they don't know anything about how they're talking to the other parts, which is, it's tough to know. I mean, it's great when one of your nodes is resource constrained. It's useful to be able to go in there and see, this is the resource that's constrained, this is why it's constrained. But when you're trying to understand the overall context of where your latency is and why you're spending all your time, it's hard to do that, right? Okay. So OS tools are great for, like I said, observing resource depletion. They're also good at diagnosing host or operating system failure. And that's totally legitimate, right? Because host or operating system failure often presents as acute performance problems. Sometimes, like, can't get an answer, right? So let's look closer, though, because real insight into the code requires instrumentation. And instrumenting means inserting code to track the behavior of your application. The first category of instrumentation I'd love to talk to you about is what I call ad hoc instrumentation. And this is where my performance career really started in building out ad hoc systems. I was working on a Corba-based service-oriented architecture, and I wanted to understand where all our latency was coming from, although maybe you've got some clues already based on what I've said. But I wrote a stats service that would record call timings and report mean latency and mean deviation on a per endpoint basis. Now, it didn't produce quite the insight that I was looking for because I didn't have as much historical data as I would have liked, and so it was hard to see the effect that the changes were having and what we could have done. But anyway, that's a different story. But it did teach me a lot about how difficult it is to write instrumentation and how hard it is to get it right. A more recent example, at my current company, we wrote an ad hoc piece of instrumentation that connects to each of our collectors. Collectors are high throughput nodes responsible for receiving inbound data, right? And they expose an API that reports on connection status. And so we wrote a little Flask app that reaches out to each of the collector nodes, aggregates the data, does some database lookups to make the data human readable, and then passes that up to a web node. And that's a sort of a specialized thing, and for specialized things, that's a pretty good approach. But there is a better way for the more general case, right? And this is StatsD. Etsy has sort of done a good, well, they've definitely done a good turn to the community by releasing StatsD. StatsD is a small server. It runs on your production nodes. And your application can shovel all sorts of labeled metrics down into StatsD. Then StatsD uploads those metrics into a Graphite interface, right? Graphite, if you don't know, is a general purpose graphing package for time series data. That'll let you trend your metrics over time. So let's see. This is an example of how you actually do the instrumentation. It's ripped straight from the StatsD package documentation. The top one is an example of doing a timer. You set up with a context manager, and as soon as the block ends, the timing for that block gets sent off to StatsD with the label foo in this case, which I'm sure will be unique in your system. And then the bottom one is even simpler. It's just a counter, some.event, which also I'm sure is a very descriptive identifier, will increment each time that line of code is called. So, and this is the kind of graph that you can expect to get out of it. This one is, what is this? Oh, sorry, it's the connections on one of our MySQL databases, right? Yeah, my speaker notes are wrong, so. But anyway, so ad hoc instrumentation works great for tracking and trending discrete events, right? If there's a specific event that you're interested in, like our number of connections on the database, or maybe mean time to process a login, or even just number of logins, ad hoc metrics are a great way to keep an eye on it, right? This approach to stats can be labor intensive because every point of instrumentation is hand tooled. You pick out the thing you want to measure, you put in the instrumentation code, and you build a graph for it. It can also be pretty exhausting to interpret because once you get above a certain number of graphs, like one of the guys I work with, he has a screen that he just keeps filled with all these Munin graphs all day long. And he's like, oh yeah, I can totally see immediately. And I'm like, whoa, dude, that's too much information. Not in the usual way. So let's see. And like many of the other tools that we've looked at, it provides data points, but it doesn't provide a real good context for those data points. So this is where tracing kicks in, right? There's a theme that's been developing, and the theme is that it's hard to see performance in context of the requests that are taking time. And this is where tracing techniques come in. So this is a trace in Twitter's Zipkin. And so a trace is based around the idea of, or rather, it's a representation of the path of execution followed in the fulfillment of a single request. So this example in Zipkin shows a 113 millisecond trace that makes use of a number of strangely named services like Quickie, web server, some service, and memcached. Oh, and big ass service, nice. But anyway, you can see at each layer that a certain amount of time is being consumed at that service layer in satisfying those requests, and ultimately the trace returns to the user. When you have these traces, you can aggregate them and trend them in visualizations. This comes out of TraceView, which is the product I work on, and it shows an application with all of the layers in that application. This one's I think it's a Django application that also talks to services implemented in Ruby, Java, and Drupal 7. And assigns latency for the requests to them. And you can sort of see, like, as time goes by, how each of those is a little bit slower or a little bit faster, depending on what's going on the system. Right on. So finally, this is actually a great place to start when you're looking at latency data. Individual traces provide a great window into which code paths have unacceptable latency, and the trace tools themselves offer a great way to see the overall latency. So you may ask, why do you wait until the end of the talk to talk about it if that's where you want to start? And the answer is, this is kind of like the architecture diagram we were using for ad hoc metrics. Oh my God, my microphone's falling. Help, help. All right, if you can't hear me, just start yelling. It's similar to the architecture diagram we used previously, but this is significantly more articulated, right? You've got your application with some kind of metrics aggregator, similar to the way StatsD works, and then an ingestion that assembles the traces, an analysis component that plucks out the meaningful parts and inserts it into the databases, and a large-scale data store to handle all of this because you're dealing with millions of events a day. Then you've got querying and statistics logic on the far side of that, plus data visualization and UI. And what's rough about this is that in general, that's not super easy to do in a very generic way for every application. You can get some of it, but a lot of it is pretty hand-tooled to the application that you're building. So in short, why do I wait to the end? It's a pretty complicated tool to build and set up. So there are some free versions out there of tracing tools, and I would encourage you all to investigate them and make them better, because right now they all kind of suck from one way or another. Google's Dapper paper is actually just a paper. You can't really run that very well. Yammer's telemetry, I understand, is functional, but a little bit hard to deploy. And Twitter's Zipkin, as far as I know, still doesn't have Python support, and it's a little bit hard to stand up all the services involved, but it's a completely viable tool. Yeah, we saw some screenshots earlier, right? If you don't want to buy it, there's free tools. My company produces TraceView. Probably most of you are familiar with New Relic. AppDynamics also makes a tracing tool. There are free plans available, I think, from all three of those vendors. And there are also paid plans where they'll manage a ton of data for you. They're nice because the instrumentation for these guys tends to be sort of a one-stop thing. You just sort of drop the packages in, and like this is a Django setup. You just import it at the top of your settings.py file, and it patches itself into place. But there are some limits to tracing, right? The graph's kind of like a limit, right? Well, this is actually a graph of a memory leak where we just restart the server periodically to clean the pool. Tracing is a great tool, but it has limits. The filtering of traces gets limited to a specific set of metadata that the tracing tool considers relevant. and the more metadata you, the more dimensionality you add to your data, the more data storage and latency you introduce into your tracing tool. Also, you either rely on probabilistic sampling, and so you can miss certain outliers, or you only catch the outliers, and so you miss the fat middle. Depending on which methodology you pick when you're tracing, you're going to miss something. It's a great place to start, but it also isn't the only way to look at your performance. In fact, it's really just a place to start in a lot of ways. So we've looked at a bunch of tools for performance management, and all of them have strengths and all of them have limits. Any of those could be the hammer, right? Instead, you got to think about them as a toolbox. You start an investigation in a tracing tool to give you the high-level insight into where in your application things are slow. Maybe you're getting some outliers, and you might want to check your hosts with the operating system tools to see if you're running into resource constraints. Maybe you filter the traces down until you find some slow, high-traffic code paths, and you switch over to a profiler at that point to look to see what code's actually causing you problems. You also always want to be tracking the key events and durations to get some insight into why things are happening instead of just how. No one tool has it all, so yeah, build a toolbox, don't pick a hammer. I have some references in the slides, including these slides, which is, I guess, a little recursive, but maybe that's helpful. And thanks.
We have time for maybe 1 or 2 questions if you want to stand up in the middle.
So, a quick question about whether you think it's better to trace explicitly or monkey patch existing instrumentation, I guess, is part one. And then part two is, do you think there's value in building the trace retrospectively from other instrument data if you have the trace ID, but it's being collected in other metric systems? Can you kind of recreate traces of interest?
So I think, let's see. If I understand the second part, it's if you've got trace data that is tagged but in multiple monitoring databases, is there value in reassembling that? And I think the trace context always helps you understand a little bit better about the why and the how the latency occurs. So if there's ways for you to assemble that, if you can make that happen, then I think that that extra context is usually helpful when you go in to try to actually solve the problem or address it, right? I'm not sure I understood your first question, though. Can you?
Well, I mean, I looked at Oboe briefly during the talk and saw that it does some monkey patching.
Right.
Which is always...
Sure.
I mean...
So the reason we do the monkey patching is essentially just to wrap the blocks that you would time with timers, and to ensure that we're passing along the trace metadata. The alternative to monkey patching, I think in this case, because many of these interfaces don't provide any other extension behavior, would be to require the application developer to explicitly have tracing in mind at every point along the way. And so I think that the monkey patching in this case probably makes a decent amount of sense. In other language instrumentations, we've rewritten the language, or we've written bolt-on modules that inject code. And honestly, Python's monkey patching makes this almost the least intrusive of the strategies.
Thank you.
Sure.
Thank you all.